Hello, this is Gregory Maxwell, and this is our lesson on complex numbers. Complex numbers are numbers that are combination of real numbers and imaginary numbers, and we will be talking about that today. As a prerequisite for this lesson, you need to know rules of exponents, how to simplify radicals, and also multiplying binomial expressions. The topic of complex numbers is a very important topic in mathematics, so we need to pay close attention to how to use this. Complex number is a number based on the imaginary number I, which is a number that when you square it, the answer is -1. It is often referred to as the square root of -1, but that is not quite precise. It is more properly defined as the number whose square is -1. And so it is called the imaginary number because there is no real number that when you square it, you get -1. However, even though it's called the imaginary number, it's a very important number. It's not a fantasy. So it is important that we know how to work with the imaginary numbers and in general the complex numbers. The complex numbers have two parts to them. Complex numbers have the real part, which is represented here by A, and the imaginary part, which is represented by B, multiplied by the imaginary number I. As I said, I is the number whose square is -1. So the real part of the complex number is A and the imaginary part is B. And the complex number in standard form is written as A plus BI. Real part plus imaginary part multiplied by I. Let's talk a little bit about the powers of I. I, by definition, is the number whose square is -1. Now, from exponent rules, we know that if we raise any number to the power 1, we get the number again. So I to the power 1 is I. And by definition, I squared is -1. So what do we do to get I cubed? Well, I cubed is I squared multiplied by I, because basically I cubed is multiplying I by itself 3 times. But I squared, we just saw by definition, is -1. So I cubed is actually -1 multiplied by I, and that gives you -I. I to the 4 is I squared times I squared, and therefore I to the 4 is -1 times -1, which is 1. So I to the power 4 is 1. I to the power 5, if we continue, you'll see that I to the power 5 is I to the 4 times I to the 1, which is just 1 times I, because we just saw that I to the 4 is 1. So I to the 6 is I to the 4 times I squared, which is, of course, I to the 4 is 1, I squared is -1, so I to the 6 is 1 times -1, which is -1. I to the 7 is I to the 4 times I to the 3, and I to the 3 we just saw is -I, and I to the 4 is 1, so I to the 7 is 1 multiplied by -I, which is -I. And I to the 8 is I to the 4 times I to the 4, which is 1 times 1. As you can see, a pattern is emerging here. Every time we go 4 units, we basically start over. That's similar to how the clock works. Every time you go 12 hours, you start over, or how the week works. Every time you go 7 days, you start over. Today, for example, if today is Monday, in 7 days it will be Monday again. So with powers of I, the pattern repeats for every time you add 4 to the exponent. And remember, I to the 4 is 1. So to simplify higher powers of I, all you'll have to do is group the fourths and then see what's left over. In other words, we look for the remainder after we divide by 4. Here is an example. I to the 33 is actually I to the 32 times I. Why is 32 so important? 32 is a multiple of 4 because 32 is 4 times 8. So I to the 33 is I to the 4 to the 8, because remember, from exponent rules, we multiply exponents when we raise a number to a power. So I to the 4 to the 8, which is I to the 32 multiplied by I. But I to the 4 is 1. So this is really 1 to the 8, and 1 to any power is 1. So all that is important to figure out what the answer is, what is the remainder after I separate the powers, the multiples of 4. I to the 33 is I to the 32 times I to the 1, which is 1 times I to the 1, and I to the 1 is I. So we can move on here to look at another example. I to the 83. I to the 83, if you divide 83 by 4, you'll get a quotient of 20 and a remainder of 3. So I to the 83 is I to the 4 to the 20 times I to the 3, and I to the 4 is 1. So this part, I to the 4 to the 20, becomes 1, and I to the 3, we just saw up here, is negative I. So if we can look at the remainders of the power after dividing that power by 4, that will give us what the answer is. Now, I just like to point out that this rule works for integer powers of I. This does not work for rational powers that are not integers, like I to the half. That is a more complicated process, and that would involve trigonometry. Now, as a general rule, to help us to figure out the integer powers of I, is the process. First, memorize these rules. The first thing is I to the 0 is 1, as it is with all non-zero numbers. Any non-zero number raised to the power 0 is equal to 1. So I to the 0 is 1. I to the 1 is I. Any number raised to the power 1 is itself. I squared is negative 1, which is by definition, and I cubed is equal to negative I, which we just saw. If you memorize these 4, you can figure out the simplified version of the integer powers of I. Now, these numbers are significant because these are the 4 remainders that you will get if you divide an integer by 4. If you divide an integer by 4 and get a remainder of 0, that means that integer is a multiple of 4. Other remainders would be a remainder of 1, a remainder of 2, a remainder of 3. Those are the only possible remainders you can get when you divide an integer by 4. Now, to figure out the simplified version of I raised to an integer power, here's the process. First step, divide that exponent by 4. Now, again, you remember you have 4 possible remainders. If the remainder is 0, that's because the number is a multiple of 4 and the other remainders are 1, 2, or 3. If your number is a positive number, write your remainder as a positive remainder. If your exponent is a negative number, write your remainder as a negative number. And remember also, if you divide by a multiple of 4, the remainder is 0, so you'll get a whole number. If the remainder would be 1, and you divide that number by 4, you'll get something 0.25. If you divide a number by 4, you get something 0.5, that means the remainder is 2. And if you divide the number by 4 and you get something 0.75, then the remainder is 3. So for example here, 379 divided by 4 is 94.75. So the remainder after dividing 379 by 4 is 3. When we divide negative 39 by 4, we get negative 9.75. So the remainder is negative 3 because the original exponent is negative 3. Now, let's take a look at the integer powers, the next step. Once we divide by 4, if you have a positive exponent, the positive remainder will tell us what the answer is. So in the first example, when we divided 379 by 4, we got a remainder of 3. So I to the power 379 is exactly the same as I to the power 3. And I to the power 3 is negative 1, as we see up here from that list that you need to memorize. However, if the remainder was negative, we need to adjust that to make it positive by adding 4 to it. And that will make it a positive. It is similar to saying, if you imagine a circle with 4 markings on it, and the marking on the top is a 0, and so you have 3 other markings. Going forward, one spot forward is the same as going backwards 3. So if you think of going backwards as -3 and going forward as positive, then going backwards -3 is the same as going forward +1 on this circle. Think about a clock. A clock has 12 spots on it. If you go forward 2 hours, it is the same as going backwards 10 hours. And the reason for that is there are 12 markings and 10 plus 2 is 12. So if you want to find out what time it was, if it is now 12 o'clock, and you want to find out what time it was 3 hours ago, right? Think of the 3 as -3 and then add 12 to that, and that will give you +9. So it was 9 o'clock 3 hours ago. Since the cycle for the exponents of I is by fours, if you go back 3 units, it's the same as moving forward -3 plus 4, which is 1 unit. So in short, if your remainder is a negative number, just add 4 to that remainder, and that will give you the corresponding positive remainder for the powers of I. So I to the -39 is the same as I to the -3, which is the same as I to the +1, and I to the 1 is I. So just to recap the steps, first divide the exponent, the integer exponent, by a power of 4, and then replace that as the remainder of that exponent. So I to the 379, for example, is the same as I to the 3 because 3 is the remainder when you divide 379 by 4. If the exponent initially was a negative, write the remainder as a negative, then add 4 to that exponent, and then use the rules, the properties of I to give your answer. Let's do some examples here. The first example we have is I to the -49. So step number 1, we are going to divide the exponent by 4. When we divide the exponent by 4, the remainder will be -1 because 49 divided by 4 is 12.25, or 12 with a remainder of 1. But since the initial exponent is negative, we're going to write that remainder as -1. Now, since the exponent is a negative remainder, what we will do then is we will add 4 to that remainder. And when you add 4 to -1, you will get a +3. And then, of course, I to the 3 is -I. So the simplified version of I to the -49 is -I. Let's try I to the 25. Again, we divide the exponent by 4. Once we divide the exponent by 4, the remainder is all we care about. 25 divided by 4 is 6 with a remainder of 1. So that's just I to the 1. Well, I to the 1 is just I, because any number raised to the power of 1 is I. And that's all. Now let's look at the third example, I to the -56. I to the -56, if you divide -56 by 4, you get a remainder of 0 because 56 is a multiple of 4. So when you divide by 4, the remainder is 0. In the first example, the remainder was -1. In the second example, the remainder was +1. And in the third example, the remainder after we divide the exponent by 4 is 0. And I raised to the power 0 is 1. Be careful that you only focus on the remainder. Now, let's move on to another property of imaginary numbers. Now, we just spoke about the powers of I. What happens when you have the square root of a negative number? If you try to do the square root of a negative on a regular or scientific calculator in real mode, the result will give you an error. Now, that's just telling you that the answer is not a real number, but that doesn't mean it's not a number, it's just not a real number. And so we have this rule here that since I squared is -1, if we want to find the square root of negative, the principal square root of -1, that would be I. As we have as an example here, we have square root of -144 is the same as square root of 144 times the square root of -1. So let me just indicate that right here. This is the same thing as square root of 144 times the square root of -1. This symbol is the principal square root, which means the positive version of the square root. So that's the principal square root of 144 is 12, and the principal square root of -1 is I. And that's the answer that is written right here. Similarly, square root of -49 is the square root of 49 times the square root of -1, which gives us 7i. Square root of -10 is the square root of 10 times the square root of -1, which is square root of 10 times I. Make sure that the I is not under the radical. Again, that's a totally different number. So to avoid confusion when we have a situation like this where the radical cannot be simplified, we put the I in front of the radical so it's clear that it's not under the radical. Now, with this example, example D, we see that square root of -48 is square root of 48 times I. Well, 48 itself is made up of a perfect square, which is 16, multiplied by a number that cannot be broken down any simpler into perfect squares. 16 times 3 is 48, and square root of 16 is 4. So square root of 48 is 4 square root 3. And of course, the negative under the square root gives us an I. And if we don't want the I to appear to be under the radical, you move the I to the before the radical. And a similar example is here, where we have square root of 84. The largest squared number that can divide into 84 is 4, and 84 divided by 4 is 21. There's no squared number other than 1 that will divide into 21. So then we end up with 2, which is the square root of 4 times 21, and of course the I. As a general rule, let n be a positive real number. We define the principal square root of -n, denoted by square root -n, as square root of n times I. And of course, I is the number whose square is -1. Let's do a few examples to illustrate. This first example, square root of -6 times the square root of -2. What we will do first is we will rewrite square root of -6 as square root of 6 multiplied by I, and square root of 2 multiplied by I is the square root of -2. Then I'll multiply the parts together. I'll multiply square root 6 multiplied by square root 2, which is square root of 12, and I times I is I squared. Now there are two things going on here. 12 can be written as the square root of 4 multiplied by the square root of 3, and I squared, if you recall, is -1. So when I simplify all of this, I get -2, because the square root of 4 is 2, square root 3. And that is it. Our next example, square root of -75 squared. Since it's the square root of a negative, we know there's an I there, so I'm going to just write that as square root of 75I. And I'm squaring the whole thing. An exponent rule says if I'm multiplying two things and I raise it to an exponent, then I distribute the exponent. So I get the square root of 75 squared multiplied by I squared. Well, the square root of 75 squared, that leaves us to cancel the square roots, and then I squared is -1. So we end up with 75 multiplied by -1, which is -75. Now if I raise square root of -75 to the power 3, that will involve a little bit more work. As before, we have the square root of 75 raised to the power 3 times I raised to the power 3. We already know that I raised to the power 3 is -I, but what about the square root of 75? This again is where we have to remember our exponent rules. So this is the square root of 75 squared times the square root of 75 again, multiplied by negative I. And the negative I is because I cubed is negative I. The square root of 75 squared gives you just 75. So we end up with 75. The square root of 75 is square root of 25 multiplied by the square root of 3. And of course, we are multiplying by negative I. The square root of 25 is 5. So we have 75 multiplied by 5 multiplied by the square root of 3 multiplied by negative I. The result then is, what do we get when we multiply 5 by square root by 75? 5 times 5 is 25, and 5 times 70 is 350. So we're looking at 375 times the square root of 3, and we're multiplying that by negative I. So we get negative 375 I square root 3. We put the I in front of the radical so that it doesn't appear to be under the radical. Next example, negative 5I to the 5. If you notice, the negative 5I is not in parentheses, which means the exponent only applies to the I, not to the negative 5. So we're going to keep the negative 5 and simplify I to the 5. I to the 5, when you divide 5 by 4, the remainder is 1, so that's I to the 1, and I to the 1 is I, so the answer is negative 5I. Next example, if we have 2I to the 3, we can do this by distributing the cubed, so we get 2 cubed times I cubed. Now 2 cubed is 8, but I cubed, we can move that to the numerator, and that will give me times I to the negative 3. Negative exponent, negative remainder, we would add a 4 to that exponent, and we get I to the 1. So the answer for this one is 1/8 I. And the reason again is we added 4 to the negative 3. Negative I to the 3 is the same as negative 1 times I to the power 3, which means negative 1 to the 3 times I to the 3. Negative 1 to the 3 is negative 1. I to the 3 is negative I. So the answer for this one is positive I. So, of course, to get the good grasp of this, it's best to do multiple examples. Now, let's get into complex numbers in more detail here. As we said before, complex numbers are made up of two parts, a real part and an imaginary part. The negative of a complex number is simply changing all the signs, making all of them the opposite. So, for example, the negative, let's use the example here. For example, the negative of 5 minus 9I is negative 5 plus 9I. You change both signs. That's the negative. The conjugate, on the other hand, which is a very important property of complex numbers, is simply the same complex number, but the sign in front of the imaginary part is changed. And we represent the conjugate by putting a bar above it. So I'm going to represent these examples. Let's call Z the complex number, just one letter to represent the whole thing. So if Z is a complex number, negative 8 minus 15I, then the conjugate is called z bar. And all that means is we are going to be replacing the sign of in front of the imaginary part with its opposite. So instead of -8 minus 15i, it will now be -8 plus 15i. And that's the conjugate. The conjugate is represented by a bar. So that's the conjugate of z. Here's another example. Let's use w this time. Let's say w is 12 minus 5i. Then w conjugate is 12 plus 5i. Now, before I do a few examples of those, I just want to point out a few rules about adding, subtracting, and multiplying complex numbers. When you're adding complex numbers, you basically add them like you would any regular arithmetical expression. We treat the I like it's a variable, but just remember whenever you have I squared or I to any integer power, that can be simplified to either 1i, -1, or -I. So when we're adding these numbers, we add the real parts together, 3 plus 5, and the imaginary parts together, -2i plus -4i. So 3 plus 5 is 8, and -2i plus -4i is -6i. And this is now in standard form. Very simple. Next example, subtracting. Just remember, when you're subtracting, you have to change the sign of the part that is being subtracted. In a sense, we're distributing this negative sign to each part in the second parentheses, and then we combine like terms. So 3 minus 5 and -2i minus -4i. And when you combine the like terms, you get -2 plus 2i. When multiplying, we use the distributive property of known as FOIL when you're multiplying two binomials, but its distributive property more precisely. We multiply 3 by 5 and 3 by -4i, -2i by 5 and -2i by -4i. And we get this result, 15 minus 12i minus 10i plus 8i squared. But I squared is -1. So we get 15. The -12i minus the 10i is the -22i. And then the 8 multiplied by I squared is -8, which you then add to the 15, that gives you 7. And so we end up with standard form again, which is 7 minus 22i. Just going to indicate again what we did here. We distributed by multiplying each term in the first parenthesis, pair of parentheses, by each term in the second pair of parentheses. Now, just a few examples to illustrate this, and then we'll go back to our instruction. For this question here, since it's a plus, all we have to do is add the real parts together and add the imaginary parts together. 13 plus -5 is 8, and -2i plus 6i is 4i, and that's it. It is in standard form, and standard form is a plus bi, real part plus imaginary part followed by I. Let's go on to this example here. When we're subtracting, remember we distribute the negative, so we end up with 3 plus 2i minus 6 minus 13i. And of course, we combine like terms, and we have 3 minus 6 is -3, and 2i minus 13i is -11i. So the answer is 3 minus 11i. And of course, this third example is very simple from there. You distribute the negative, you get 13i minus 14 plus 7i. And we put the real part, since there's only one real part there, we'll just put -14 first, and then 13i plus 7i is 20i. Then A little bit more complicated example here, where you're going to distribute this negative inside this parentheses, this pair of parentheses, and then we will combine like terms. Negative 3 halves plus, minus 5 halves I plus 5 thirds plus 11 thirds I. Negative 3 halves plus 5 thirds. So of course we'll have to get common denominator of 6 here. So we're going to multiply the numerator and denominator here by 3. We get negative 9 over 6. And then multiply the numerator and denominator by 2. We get plus 10 over 6. And then for the i's, we multiply numerator and denominator of this part by 3. We get negative 15 over 6i. And multiply numerator and denominator by 2, we get plus 22 over 6i. Combining like terms, negative 9 over 6 plus 10 over 6 is 1/6. And negative 15 over 6 plus 22 over 6 is 7/6 I. And that is the remainder. The last example from this set, we will now rewrite this in complex form. So I'm going to rewrite this as negative 2 plus square root of 8 times I plus, and since there's just a plus, I just don't need the parentheses, 5 minus square root 50 multiplied by I. Now the square root of 8 can be simplified as square root of 4 times square root of 2, and the square root of 50 can be simplified as square root of 25 times square root of 2. And then that means I have negative 2 plus 2 square root 2 times I plus 5 minus 5 square root 2 times I. So negative 2 plus 5 is 3. 2 square root 2 plus minus 5 square root 2 is negative 3 square root 2, and of course I. Or you could write that as 3 minus 3i square root 2, so that the I doesn't appear to be under the radical. Please make sure you write your I's a little clearly. Mine is a little messed up here, but you get the idea. Seeming to be having a little trouble with my I. All right. Let's move on to some more examples. This time it's multiplication. And the rules of exponents apply as before. We're going to distribute the monomial by each term in the parentheses. So we have negative 8i times 9 is negative 72i. And negative 8i times 4i is negative 32i squared. But I squared is negative 1. So we have negative 32 times negative 1, which is positive 32, which is the real part. So we put that first, and then we put the imaginary part afterwards. And that's it. Next example. This is what we usually refer to as FOIL, first, outer, inner, last, but it's really just the distributive property. So 6 multiplied by 2 is 12. 6 multiplied by negative 3i is negative 18i. Negative 2i multiplied by 2 is negative 4i. And negative 2i multiplied by negative 3 is positive 6i squared. And these two are like terms, so we put them together. And this is negative 1. I squared is negative 1. So you end up with 12 minus 22i, and then minus 6 because I squared is negative 1. And then combining like terms again and putting the real part first, we end up with 6. 12 minus 6 is 6, and then minus 22i. And that is our answer. Next example. When you're squaring something, you're really multiplying it by itself. So I'm going to write this as 2 minus square root of 6 multiplied by I, because that's square root of negative 6. And I'm going to multiply it by itself. Please remember to make sure that the I is not under the radical. I do the distributive property. 2 multiplied by 2 is 4. 2 multiplied by square root 6, negative square root 6 is negative 2 square root 6. And then, of course, the I. And then negative square root 6i times 2 is another negative 2 square root 6 times I. And then negative square root 6 times negative square root 6 is positive square root of 6 squared. And that's times I squared. Simplifying, we get 4 minus 4 square root 6i. And then the square root 6 cancels with the square, leaving 6, and the I squared is negative 1. So we end up with negative 6. So our result overall is negative 2, because we combine the 4 times the negative 6, minus 4 square root 6 times I. Next example. We're going to distribute as before, and when we do so, we'll simplify afterwards. Well, let's simplify now. So this is 3 plus square root 5 times I, and multiplied by 7 times square root 10 times I. Distributing, we end up with 3 times 7 is 21. 3 times negative square root 10 is negative 3 square root 10, and then multiplied by I. And then square root 5i times 7 is positive 7 square root 5 times I. Please be sure that you don't multiply what's outside with what's inside the radical. Very dangerous. And then this is minus square root 50, because you can multiply what's under the square root by what's under the square root. And then I squared, because that's I times I. Combining like terms, we get 21 plus, well, these are not like terms. So all we can do is say, let's put that as a plus parentheses 7 square root 5 minus 3 square root 10. And then both of those have an I. So I essentially factored out an I. And then over here, we have square root of 50, which is the square root of 25 times the square root of 2, and then times negative 1. That whole thing is going to be combined with the 21 to give you 21 plus 5 square root 2, and that becomes our real part, and it's a plus because negative times negative 1, and then plus the imaginary part, which is 7 square root 5 minus 3 square root 10, and all of that multiplied by I. That one was a little tedious, but if you do it step by step, it works out. Last example here, we have 2 plus 3i squared plus 2 minus 3i squared. So we have to square both of them. So we have 2 plus 3i times itself, and then plus 2 minus 3i times itself. And of course, PEMDAS says we should do the multiplication before we do the addition. So I multiply 2 times 2 is 4, 2 times 3i is 6i, and 3i times 2 is another 6i, and 3i times 3i is 9i squared. And over here, we have 2 times 2 is 4, 2 multiplied by negative 3i is negative 6i, and negative 3i times 2 is another negative 6i, and negative 3i times negative 3i is positive 9i squared. And as you can see here, we can actually do 6i cancels with negative 6i, and both of those i's disappeared. And so what we end up with is 4 plus 9 times negative 1 plus 4 plus another 9 times negative 1. So 4 plus 4 minus 9 minus 9. That's 8 minus 18, which is negative 10. So the answer is negative 10. And that is how we multiply, add, and subtract. Now, these examples simply say write the complex conjugate of the complex number, then multiply the complex number by its conjugate. So let's see. The conjugate, I'm going to call this complex number z. So let's say z is that. So z conjugate is simply 6 minus 3i. And now let me multiply z times its conjugate, and I will get 6 plus 3i multiplied by 6 minus 3i. And if you remember, the conjugate is the same complex number but with the imaginary part, the sign changing for the imaginary part. So when we multiply, we get 6 times 6 is 36. 6 times negative 3i is negative 18i. 3i times 6 is positive 18i. And then 3i times negative 3i is negative 9i squared. And then we end up with 36. And it turns out that this is a difference of squares, so those will cancel. And then we have positive 9, and that's because I squared is negative 1. So basically it's 6 squared plus 3 squared, which is 36 plus 9 is 45. And that's our answer for that. Let's do this next one here. Let's call this complex number W. So W is 7 minus 12i, so W conjugate is 7 plus 12i. And we multiply. And while I'm multiplying this, I just like to suggest that I would recommend that you try to do these questions on your own before you look at my process of solving these, because then that will allow you to check to see if you understand the concept. Then you can check the video. You can pause the video, do the exercise, and then check the video again to see if you got it right. So I'm going to multiply 7 minus 12i by 7 plus 12i. And as you can see, that looks like a difference of squares again. So we multiply 7 by 7, that's 49. And then 7 by 12i, that's positive 84i. And then minus 84i. And then minus 144i squared. And then that gives you 49. The 84i and the negative 84i cancel, as occurred in the previous. And then that's just positive 144 because I squared is negative 1. Again, 7 squared plus the square of negative 12. And then when we add those up, I believe that gives us 4 plus 9 is 3. And 4 plus 14 is 193. I believe that's what that works out to be. Now let's go for the next one. Let's call this U. So U bar or U conjugate is negative 3 minus square root 2i. So when we multiply U by its conjugate, we get negative 3 plus square root of 2i times negative 3 minus square root of 2i. And some of you may be able to notice what's going to happen again here. Negative 3 times negative 3 is positive 9. And negative 3 times negative square root 2i is positive square root 2i. Apologize, positive 3 square root 2i. And then positive square root 2i times negative 3 is negative 3 square root 2i. And then square root 2 times negative square root 2 is negative square root 2 squared I squared. And when you square a radical, it cancels. So we end up with 9, and then the i's cancel, and that leaves us with 9 plus 2 because I squared is negative 1. And then again, square root of negative 3 and square root of square root 2 gives us 11. Now let's take a look at this one here. This one, let's call that let's go back to Z here. So Z really is square root 20 times I, also known as 2 square root 5 times I, because square root 20 is square root 4 times square root 5. So the complement, the conjugate is negative 2 square root 5 times I, because that's the imaginary part. So when we multiply them, z by z conjugate, we get basically uh, 2 square root 5 times I times negative 2 square root 5 times I. That gives us negative 4 times 5 times I squared. And that gives me a negative times a negative is a positive, and a 4 times 5 is 20. Some of you may have noticed that if you just kept it like this, square root 20 times I, you just get negative square root 20 times positive square root 20, which gives you negative square root negative 20, and then times I squared. Gives you the same result. And that's that. Then for this one, there is no I because that's not the square root of a negative. So if this is, say, P, then P conjugate is just itself, because the imaginary part is 0 and positive or negative 0 is the same result. So if we multiply these numbers by the number by its conjugate, it's really 1 plus square root 8 multiplied by itself. When we multiply those, 1 times 1 is 1, 1 times square root 8 is square root 8, 8 times square root 8 times 1 is another square root 8, and square root 8 times square root 8 is square root 8 squared, which is just 8. 8 plus 1 is 9 plus 2 square root 8. Or you could probably simplify that as 9 plus 2 square root 2 times 2 square root 2, which is 9 plus 4 square root 2. Either way, we just get a regular real number and we have no imaginary component. So at this point, we only have, let's quickly recap a few things here. If you may notice, the definition of conjugate of a complex number is to change the sign in front of the imaginary part. When you multiply a complex number by its conjugate, all you're doing is adding the squares of the real part and the imaginary parts. And the conjugate of a real number is itself. The conjugate of 5 is 5. The conjugate of negative 7 is negative 7. Another few rules here. The conjugate of the conjugate is the original complex number. This one was not explained, but you can see it relatively easily. If you multiply the conjugate, if you add the conjugates, if you add two complex numbers and then find the conjugates, you can just add the conjugates directly. And then if you multiply two complex numbers and find the conjugate, it's the same as multiplying the conjugates. Those I did not show how those rules came about, but it's good to know them. All right, before we go to the division of complex numbers, let us quickly do a few more simple examples here. So, first of all, I cubed. We know that I cubed is negative I. So this is 4. I cubed is 4 times negative I. And we know that I squared is negative 1. So we end up with negative 4I plus 2 plus 1, which in standard form is 3 minus 4I. Very easy. I to the 7, if we divide 7 by 4, the remainder is 3. So we get I cubed. And I squared is negative 1. So we end up with negative I, because that's I cubed, times 0. And anything times 0 is 0. For this one, we distribute the exponent because that's a product raised to our power. So we get 3 to the 4 times I to the 4. And I to the 4 is I to the 0, because when you divide 4 by 4, you get the remainder of 0. And 3 to the 4 is 81. So basically, it's 81 times I to the 0. I to the 0 is 1, so it's 81 times 1 plus 1, which is 82. Now we're multiplying here. As you can see, these have opposite signs, but not in front of the I. So let's see what ends up happening here. Negative 3 times 3 is negative 9. Negative 3 times I is negative 3I. I times 3 is positive 3I. And I times I is positive I squared. The middle terms are opposites, so they cancel. So you end up with negative 9, and I squared is negative 1. Negative 9 plus negative 1 is negative 10, which is the negative of what you would get if you multiply the conjugates. And that's because this is the negative of the conjugate of this. So that is expected. Now, let's see what we get when we raise it to the power 3. And of course, raising something to the power 3 means you're multiplying it by itself 3 times. So we use the associative property here. We multiply the first term times the second term, and then we'll multiply the third afterwards. So we're going to multiply 1 times 1 is 1. 1 times I is I. 1 times I again is I, and I times I is I squared. So we end up with 1 plus I plus I plus I squared. And we're going to multiply that 1 plus I afterwards. And so we end up with 1 plus 2I minus 1. And 1 minus 1 is 0, so this is just 2I minus 1, 2I plus 0. And then we're going to distribute that 2I to the other pair of parentheses. And that, I'm going to just continue it right here, is equal to 2I minus 2I squared, which is 2I minus 2 times negative 1, which is positive 2 plus 2I. And there you have it. Now, let's talk quickly about dividing complex numbers, and then that will be the end of our lesson. When you're dividing complex numbers, it's simple. We just don't want a complex number in the denominator, so we're going to multiply the denominator by the conjugate of the denominator. But if you multiply the denominator of a fraction by a number, you must multiply the numerator to keep the fraction the same value. So we're going to multiply the denominator and the numerator of this complex number division by the conjugate of the denominator. And then we're going to distribute. And if you remember, if you multiply a complex number by its conjugate, you get the squares, the sum of the squares of the parts. So 5 squared plus negative 4 squared. 5 squared is 25. The square of negative 4 is 16. So the denominator would simply be 16 plus 25, which is 41. The top we distribute as before, and that gives you 15 plus 12i minus 10i minus 8i squared, which I squared is negative 1. So combining like terms, we get 23 plus 2i over 41. We split the fraction, and we end up with 23 over 41 plus 2 over 41i. So the only real deal here is to remember to multiply the numerator and denominator by the conjugate of the denominator. And then you can proceed as usual and simplify. Let's do a few examples here, and then that will be the end of our lesson. For this first number, we're going to multiply by the conjugate of the denominator, which is, since the denominator is just negative 2i, we're going to multiply by the conjugate, which is positive 2i. And I'm just going to use a different color here to indicate what we're multiplying by. Now, when I multiply the numerator, I have to distribute, so I get 2 times 2i is 4i. Negative I times 2I is negative 2I squared. The denominator is negative 2 times I times positive 2I is negative 4I squared. So let's do a little simplifying here. We end up with 4I plus 2, because I squared is negative 1. And then negative 4 times negative 1 is positive 4. Simplifying then, we get 1 over 2 plus 4i over 4, which is just I. And of course, I put the real part first because standard form. Now, that's the end of that example. Let's do the next example. Again, we're going to multiply by the conjugate of the denominator, which in this case is 3 plus 4i. We multiply 3 plus 4i to the numerator and the denominator. And when I distribute the numerator, I get 10 times 3 is 30. And 10 times 4i is 40i. The denominator is 3 times 3 is 9. And of course, when you multiply a complex number by its conjugate, you simply add the squares of the parts. So we end up with 30 plus 40i in the numerator. And in the denominator, we get 9 plus 16. And 9 plus 16 is 25. So you end up with 30 over 25 plus 40 over 25i, which simplifies to be 30 over 25 is 6/5. 40 over 25 is 8/5 I. And that's our division. Again, before I do this example, the last one, I recommend that you pause the video and try the question on your own and then check to see if you get the same result as I did and if the process you followed was correct. So we're going to multiply the denominator and the numerator by the conjugate of the denominator, which in this case is 1 plus 2i. And we're going to proceed as before. Again, this is simple arithmetic, simple algebra. And don't forget your parentheses because those are very important. We distribute the numerator. We get 6 times 1 is 6. 6 times 2i is 12i. Negative 7i times 1 is negative 7i. And negative 7i times 2i is negative 14i squared. The denominator, we simply get 1 plus negative 2 squared. 1 squared plus negative 2 squared. So we get 6, 12i minus 7i is 5i. And negative 14i squared is positive 14. And at the bottom we get 1 plus 4. So combining like terms, we get 6 plus 14 is 20. And we have plus 5i, all of that over 5. That gives us 20 over 5, which is 4, and 5 over 5, which is 1, 1i. That is the answer from doing that division. Let's quickly go on to the next example here. We have 2 examples, and that will be it. This example looks a little bit more complicated, but it's actually relatively simple if you do it a step at a time. First step is work out the exponents. 5i divided by 2 plus 3i squared. You work out the 2 plus the 3i squared, which is multiplied by itself. In doing so, you end up with 5i over 2 times 2 is 4, 2 times 3i is 6i, 3i times 2 is another 6i, and 3i times 3i is positive 9i squared. Be careful that you don't cancel. Those are like terms with the same sign, so we do not cancel those 6i's. We add them together. We get 4 plus 12i minus 9. So we end up with 5i over negative 5 plus 12i. So now to do that division, I'm going to go down to the bottom line here. I'm going to take negative 5 plus 12i, and if you notice I wrote that in standard form so that I don't make an error when I'm doing the division. And I'm going to multiply by the conjugate of the denominator, which in this case is negative 5 minus 12i. So when I distribute the top, I get 5i times negative 5 is negative 25i. And 5i times negative 12i is positive 60i squared. Denominator, multiply by conjugate, so I get the square of negative 5 plus the square of 12. So we end up with negative 25i minus 60 because that I squared is negative 1, and we get 25 plus 144. We add those together, we get 13. So I have negative 60 minus, sorry, not 13, 13 squared. Negative 60 minus 25i divided by 169. In standard form, then, that would be negative 60 over 169 minus 25 over 169i. And that's our answer. It looks a little complicated, but if you do it step by step, showing all your steps, it works out much easier. And now for our final example, we're adding two divisions. And this is like adding fractions, adding two algebraic fractions. Treat the I like it's a variable, and then we'll simplify afterwards. So what we're going to do is we're going to get a common denominator. Actually, let's try it a different way. What we'll do is we'll work out the divisions first, and then we'll add. That should work fine as well. So we're going to do I over 3 minus 2i, and we're going to multiply the numerator and denominator of that by the conjugate of the denominator. And then we will do the same with 2i over 3 plus 8i. We're going to multiply by the conjugate of the denominator of that fraction. And then we're going to simplify. So we multiply, and we end up with 3i plus 2i squared in the numerator of the first fraction, and the denominator is 3 squared plus 2 squared. And then for the other fraction, we end up with 6i minus 16i squared over 3 squared plus 8 squared. Let's do a little simplifying here. We have 3i minus 2 over 9 plus 4, which is 13, and then 6i plus 16 over 9 plus 64. So basically what we end up with is negative 2 over 13 plus 3 over 13i plus 16 over 73 plus 6 over 73i. Now, using fractions to combine the like terms, remember that we need the common denominator. So we're going to put negative 2 over 13 plus 16 over 73, and we'll put 3 over 13i plus 6 over 73i. You can just use your calculator to work that out. Negative 2 over 13 plus 16 over 73 is 62 over 949. I used my calculator to do that if you're wondering. And then 3 over 13 plus 6 over 73, that gives us 297 over 949i. Prefer to leave them as decimals, I would prefer to leave them as fractions, not as decimals. And of course, you can go on to work with these videos and understand the concepts further. Please use Khan Academy to help you with some of these. The Khan Academy videos are excellent in understanding these concepts. Here are some recommended Khan Academy videos for you. You can just search them up by topic, or you can go to the link that is indicated in the video. For example, there's a video on the intro to the imaginary numbers, 5 minutes. Simplifying roots of negative numbers, 4 minutes. I as the principal root of -1, 7 minutes. Intro to complex numbers, 5 minutes. Those are all nice, easy, bite-sized videos. We also have plotting numbers on the complex plane, which was a 1-minute video. How to classify complex numbers, that's a 5-minute video example. Adding complex numbers and subtracting complex numbers, that's 1 minute and 2 minutes respectively. And multiplying complex numbers, that's a 5.5-minute video. Complex number and its conjugates, 4 minutes. Absolute value of a complex number, 3.5 minutes. And of course, dividing complex numbers, 5 minutes. Watch those videos, practice the exercises, and then that will help you to have a better grasp of the concept. That's all for the lesson on complex numbers. You can, of course, skip the parts of the video that you already understood, or review it at your own pace. And I recommend after reviewing this video, you practice carefully the concept, the exercises, so that you have a better grasp of the concept. Okay, goodbye.